3.3, applications of linear programming. Basically, that means story problems. Okay. The hardest thing that people have to do, I think, or the hardest thing for my students is just setting up the problem. All right. So let's read through this thing real quick. You're probably going to have to read it more than once. Example 1. Andrew Crowley plans to start a new business called River Explorers, which will rent canoes and kayaks to people to travel 10 miles down the Clarion River in Cook Forest State Park. So you can already see there's a lot of extra information that's not needed. So make sure, when you read it through a second time, try to filter out all the non-essential info. He has $45,000 to purchase new boats. He can buy the canoes for $600 each and the kayaks for $750 each. His facility can hold up to 65 boats. The canoes will rent for $25 a day, and the kayaks will rent for $30 a day. How many canoes and how many kayaks should he buy to earn the most revenue if all boats can be rented each day? So there's a lot going on there, and I think a lot of students will just kind of read that and be overwhelmed, okay? So don't be overwhelmed, but I think what you should do is kind of go back and look what one of the problems is supposed to look like. All right, we're either trying to maximize, and we're going to have maximize and have an objective function, and we're going to have all of these constraints subject to a bunch of inequalities. Could be a minimized problem, but this is kind of what we're shooting for. This is what we want it to look like. All right, so you got to understand that before you start, because if you don't know what it looks like, then you're going to have no way to do this problem. So back to this one. There's a lot of information there, a lot of useless information, but a lot of good information too. I think when you're looking at a story problem, a lot of the times you should start at the end. Look at the last sentence, specifically the question. How many canoes and how many kayaks? That tells me my variables. Let's call canoes X and kayaks Y. How many canoes and how many kayaks should he buy to earn the most revenue? Okay, so check it out. The most revenue. Do you think we're maximizing or minimizing in this problem? Maximizing. This is going to be a maximized problem. Okay. So we can go back through and try to cut out some of the non-essential information or whatever. All right. So we're maximizing revenue. So can you find numbers that are talking about revenue? 10 miles, no. $45,000 to purchase new boats. Well, purchasing a boat, that's not revenue. He can buy the canoes for $600. Well, if he's buying something, that's not revenue. But when it talks about he will rent them for $25 a day and $30 a day, that's the money that he's making. That's what revenue is, okay? So we're trying to maximize revenue. So what I'm going to do here is I'm going to call my objective function. I'm going to actually use the letter R for revenue. Okay, now again, go back and look at what the problem is supposed to look like. Maximize Z equals 3x plus 4y or whatever this says. It's going to look something like this. But you don't have to use Z. A lot of times people will use Z, but I'm going to use R just to remind myself that it's revenue that we're talking about. But remember, canoes was X. And kayaks was Y. So if we look at that sentence right there, it's going to be 25X. Hopefully I have enough room here. Plus 30Y. Let me move this over. Can't grab it. There we go. Okay, that's a pretty good start. That's a good start, okay? But again, look at the problem. Subject to, you've got all these constraints. Subject to, and then you're going to have all of these inequalities. So we go back through and look for some kind of limitations or constraints. So 10 miles down the Clarion River, really that number's kind of just there to throw you off. That's not talking anything about how many canoes or how many kayaks. We're not doing anything in this problem about distance. So 10 miles, that's just there to kind of throw you off. I'm not going to use that number at all. He has $45,000 to purchase new boats. Okay, now we're talking. Can he spend $50,000? He's got a limit there, right? Can he spend $44,000? Sure. In fact, if you think about this as an inequality, he can spend anything that's less than or equal to $45,000. That looks like a constraint to me, okay? So I'm going to say subject to, okay? And then 45,000 to purchase new boats. I know something's going to be less than or equal to 45,000. Okay, but if you look at talking about purchasing new boats, it says he can buy the canoes, that's X, for 600, and the kayaks, that's Y, for 750. All of those numbers are talking about buying new boats. Okay, so $600 for canoes, 600X. And 750 for the kayaks, that's plus 750y. That's one of my constraints, okay? That's one of my inequalities. Bless you. Let's see, what else do I have? His facility can hold up to 65 boats, okay? So think about what that means. Up to 65 means, can he have 64? Yes. Can he have 66? No, that's an inequality. It's talking about less than or equal to 65. But notice they don't give you any other numbers, okay? But they don't need to. We've seen an equation like this before. That's a total of 65. Something plus something has to be less than or equal 65. Well, they're talking about the number of boats. And that's what X and Y are. The number of canoes plus the number of kayaks has to be less than or equal 65. So X plus Y is less than or equal 65. Okay? Now, that's really everything mentioned in the problem. But again, go back to what it looks like. These last two inequalities are almost always going to be necessary on a story problem like this. Okay? Does anybody know why we need these in our story problem? Okay. In a real world example like this, we're talking about a countable number of objects, like the number of canoes or the number of kayaks. But in algebra, when we solve equations or inequalities that are theoretical, we might end up with negative numbers, negative solutions, okay? And so since this is a real world problem with a countable number of objects like canoes and kayaks, we can't possibly have a negative answer, right? We couldn't have like negative 50 canoes and positive 75 kayaks or something. We're not allowed to have a negative number. So we almost always on these problems will have these extra two constraints. X is greater than or equal 0 and Y is greater than or equal 0. Simply to force canoes and kayaks to be positive numbers, all right, because it's a real world situation. Now, my problem looks like what it's supposed to look like, okay? And now that it's set up, we can do what we did yesterday, all right? But here's where Desmos is going to come in, okay? I think you should use Desmos to graph this because these numbers are kind of big. I don't know that I really want to do this by hand. You can do it exactly the same way as what we did before, but let's check out Desmos, okay? Remember, I'm not graphing the equals. I'm not graphing the equation. I'm only graphing the inequalities when we do the method of corners. So my first one, 600x plus 750y is less than or equal 45,000. Okay. Oops, another 0. Okay, so zoom out a little bit. You can see that crosses at 75 and that crosses at 60 right there. All right, that's good. We've got another one, bless you. X plus y is less than or equal 65. Okay. So it gets kind of confusing when you've got two things overlapping. All right. Sometimes I think it helps if you change them all to the same color, because what we're looking at is the darker region. All right. What's been shaded twice is the darker region. But the problem here is you've got all these negative numbers. And so that's why we also have to say x is greater than or equal 0 and y is greater than or equal 0, so that we force it to be positive. Okay. Again, if you'll change everything to the same color on Desmos, your answer is the region that's been shaded all 4 times. Okay, the darkest region. And that's this quadrilateral shape right here. So let's zoom a little bit, maybe, if we can. Oops. Okay. And basically, we want to know these corners. I can find it right there, 2540. Okay, perfect. Okay, perfect. That's what I've got. So, you know, if you were doing this on your computer screen, maybe you could do a cut and paste. But we need to transfer this picture over to our work. And so notice I did not give you graph paper. And I did not give you graph paper on purpose because I think sometimes when the numbers are big, it's easier just to draw it yourself. So we only need the first quadrant. I'm only going to draw the first quadrant of this graph. And I don't need to do tick marks. Okay, this is kind of just a quick sketch. So you see how one of them goes from 60 to like, I don't know, 75 or something like that. Okay. One of the lines went like this, and one of them was a little steeper and went like this. Okay. And that's really all we need to do. I would label the corners. You had, well, I guess we could do the vertical and the horizontal. Okay, you got these corners right here. And don't forget to shade the feasible region. The feasible region is the set of all the points that could possibly be answers. Okay, anything outside of this quadrilateral shape could not possibly work. You've got negative numbers, you've got two numbers that are too big, you've got all these numbers that don't work, but inside that colored region are the numbers that work. Well, we learned yesterday that if there is an optimum value, it has to be at one of the corners. Okay, the method of corners tells me that it had to be at those corners. So, hang on a second here. Okay, 0, 60. Look at those corners, 25, 40, 65, 0, 0, 0. I'm going to label those corners. Okay. And that's basically most of my work. Okay, make sure you label the corners. Make sure you color in the feasible region. But the last step is to actually maximize. Okay, so the payoff here is we need to take this objective function here and actually find the one that produces the maximum revenue. So plug those numbers in. So 0, 0 is obviously going to give you 0, but you have 25 times x plus 30 times y. That's a 0. Oh my gosh. Equals 0. And 65, 0. So 25x plus 30y That's going to be 25 times 65 is 1625. And up top left, you got 25x plus 30y. That's going to be 1800. And 25x plus 30y equals 1825. Okay. So after that, yes, question?
Why is that 60 at the top? Why is that not 65?
Because this corner point where this intersection is 0, 60, right? If you were looking at this point, that's 65, but that's not in the region that we're looking at, okay? If you look at my graph, look at my graph real quick, okay? So the quadrilateral right here goes to this point at 60, and you might have been looking at this point at 65, but that's not less than. Remember, it had to be less than or equal both of those two lines. So we had to go lower than this line, which puts us here. Okay. All right. So we're pretty much done. Basically, we just have to actually find the maximum. Well, that's easy. The biggest number is 1825. So that's your maximum right there, right? So the last thing I would do is just write the answer. Max R revenue equals $1,825 at, well, let's not say at, okay? You could say at 2540, but since this is a story problem and it's got context, I'd put the answer back in context. 25 what? What's X stand for? Canoes. And 40 what? 40 kayaks. So I would say when you've got context in the problem, it's a story problem, make sure you put context with your answer. Maximum revenue is $1,825 with 25 canoes and 40 kayaks.